morning, everybody. My name is Coenraad, and my project for this year is the toroidal propeller test. Now, my motivation is about a month ago, a video came out from MIT, Lincoln Lab, of them showing off their new design of a toroidal propeller. A new design of propeller that looked pretty funny from its traditional counterpart. And about a week later, YouTuber channels came out with their video testing their own homemade toroidal propellers, but they had flaws in their testing. For instance, they compared a 3D printed propeller with their tri-blade injection molded propeller, and it ended up with flaws in their testing, considering that not all variables were controlled in these testing. So my problem statement here is to build an Arduino-controlled testing module for measuring the efficiency of the toroidal propeller against a traditional one, to assess whether it is more efficient than the other. Now, for my description, the MIT student Tommy Sebastian designed this propeller, and his design claims to be more efficient and more silent than its traditional counterpart. This project ended up winning him the R&D 100 award. Now, for his background, he claims that his motivation around this was derived from the early 20th century aircraft, where people had the idea of making looped wings in order to minimize wingtip vortices. Now, there are already existing designs. The Sharrow Marine LLC company is a boat propeller company making these, and their propeller patents go as far back as 2013. So, if it the legality and how much of his idea is solely his idea there's a gray area about that. Here's my sketches. This is my stand, my thrust stand. Here's the load cell, so that the propeller would go and the stand would push down on the load cell in order to measure the amount of thrust that this propeller could give. Here are my 3D models that I did. Here's my traditional propeller. As you can see, it is a 6-blade propeller in terms against a 3-loop toroidal propeller, because the surface area of one loop is almost the equivalent of 2 blades, and the specific description for a toroidal loop is 2 blades coming together at a point and joining in the middle. Here is my real model. Here's my stand with my load cell. There is a spacer in order to make the to enable the load cell to flex. And here you can see poor cable management, my toroidal propeller, and my traditional counterpart. My testing involved spooling up the propeller progressively in order to measure the amount of thrust it would give on the load cell compared to the amount of current that it needed to be able to make the thrust. And here is a video of us testing the thrusts. As you can hear, Coenraad is very scared in the background.
I smelled smoke.
Is the volume on?
Yeah, it is.
Was it full? It's very soft. Yeah, soft. Yeah, just on the right.
Before I play, keep in mind there is going to be a little bit of a rattle. That is a problem with my stand that I will be discussing later. Okay, so here's my efficiency map. just to say, this is the this is the data that I collected. Here is the acceleration of the motor, and here is the amount of thrust that it gives. So just just to specify, the electrical power was calculated, and the amount of thrust is seen on this graph. I used algebra to equalize the amount of electrical power between the two tests in order to make these two thrust values comparable. So, for instance, in my example, you can see the toroidal propeller's amount of electrical power is 1.5 times the traditional propeller's electrical power. That would be, to make these comparable, I would multiply the traditional propeller's thrust by 1.5 to see which one is, in fact, more efficient. And the ideal function for the ideal calculation for more efficiency would naturally be then providing more thrust with the same amount of electrical power used. Problems with testing the axle in this propeller had been a little bit too small for the bearings, and this caused a vibration. Now, naturally, inefficiencies in my blade's weight and the acceleration did cause vibrations, and it showed up in this data, as you can see here, if you look closely. Now, the extrusion bracket was too weak, and the extrusion it enabled the extrusion to be able to bend slightly, as you can see here. Excuse me. Just picking up the stand so everybody can see properly. Now, it does have a bit of a wiggle, but this is the part that was too weak. Okay, we just take it out. And the base was very lightweight, so we needed to be it needed to be clamped to a table in order to do proper testing. Now, here are my results that I got from the data. At a pitch of 15 degrees, the toroidal propeller made 14.85% more thrust than the traditional propeller, so already success. At 20 degrees, it did 3% less thrust. At 25 degrees, it did 0.23% less thrust. And at 30 degrees, it did 6.6% more thrust. An ideal would be more testing needed, but from this data, you could see that the toroidal propeller is good for fixed pitch blade drones, and it could also have an area that it would be good for in aviation, considering the low pitch high performance. Now, here's my product structure model. On the base, I had a low cell spacer between the low cell and the base, and the low cell attached to it. I had two stands with an axle through and bearings, as you can see here. The extrusion bracket was attached to two aluminium extrusions, one going to the low cell and another having a motor bracket attached to it. Now, for my motor, I had the motor bracket, I had the motor attached to the motor bracket. These two blade brackets are to keep the blades in between them, and through friction prevent the blades from moving from different pitches, causing inefficiencies in the test. Now, my blades here are 1 to 6, optional to 1 to 3, as it was 6 blades compared to 3 loops. And my technical difficulties are that I need to make modifications to the airfoil. Now, the angle of attack for the airfoil was printed at 45 degrees because 3D printers, especially FDM machines, really struggle with printing at overhangs over, say, 60 degrees, and it did give me problems printing anywhere from 60 up, actually 45 up, and I made the trailing edge flat. This is preferably quite bad for airfoils, but this 3D printer needed better bed adhesion, so I did cut down the trailing edge. Sorry. The design of the airfoil, although a thinner design of airfoil is better, I needed to make it more thickened because 3D printers don't have a very big resolution, and it needed to be thick in order for the 3D printer to be able to print it. Now, for my first stand, the axle was loose, causing vibrations. The extruder bracket was not big enough and weak, causing a flex in the strand. And the low cell was not properly calibrated, causing inaccurate measurements. Now, comparing the two propellers, the low cell didn't need to be calibrated, but in order for me to see the precise amount of thrust that it did give, the low cell needed to be accurately calibrated. Now, my technical successes is that the thrust stand did prove that toroidal propellers are more efficient at some pitches than the traditional propellers, and it did not blow up in our face. Lessons learned: try and keep size in mind actually when you are designing, because a lot of parts came out very, very small compared to what I wanted it to be. Follow the projected time management, because in the end I needed to go back and do a lot of things in this project that could have been finished. Here's my bill of materials. As you can see, there's a lot of 3D printed parts, with my total amount of blades going from 7 Rand to 4.5 Rand. And here are the electronics, with my total of 616 Rand. Here are my references, the YouTube videos that I watched of their testing done wrong, and the official project document from MIT. My work distribution: the majority of the work, the designing, building, and testing was done by me. The electrical, because this is a mechanical term, was done by Nick, the coding and helping with the testing. So I would say Nick probably did 50% of the work and me doing 48% more. But yeah, Benny helped me with cutting steel rods and perspex. So some of the work was done by Benny. Here's my activity log. As you can see, my tutorial project took up the most time, and some of my design project also took very long time. The PPD didn't take very long, but a lot of personal growth was done in it. I spent a lot of time working for Automation Works next door with David and Beatrice, and also going out to schools giving presentations. My theory also took somewhat a very long time, and the extra was work done by me at home that needed to be finished before deadline. Here's my poster. If you would like more information on this poster, you can see it on the wall over there. And my acknowledgements are for Nick, for the coding, the electronics, and always being there if there was help needed. For JC, for interesting conversations during PPD, and for teaching me critical thinking, which ended up helping me a lot in the future. For Benny for giving me this opportunity for learning. For Benny for helping me cutting the materials. For my classmates for helping me with some computer functions and my very forgetful mind. And for my monoprice 3D printer for not burning my house down. Thank you for listening. Any questions?
Yes, I have a question. Did you consider the standard testing rigs that are usually used for fan testing?
Yes, but I was given advice against it due to it being difficult to be able to build.
Okay.
Yeah.
And then one more question. I understand that the purpose of this project was to compare Toroidal and traditional propellers.
Yes.
Do you have a sketch that compares the two? That compares the two efficiencies?
Efficiency, a graph. Yes, I do have multiple graphs, and here in my. Sorry, can I speak in Afrikaans?
Yeah.
Okay. So I get 'n klomp foto's van die grafieke, en hierdie was net my opsomming gewees. So ek het Excel spreadsheets wat ek uitgewerk het spesifiek hoeveel krag hulle vat. So as jy belangstel daarin, dan sal ek weer nooit kan wys.
Would you be letting the people on YouTube know that their design is faulty?
Yes.
Nicely done.
Ek wil net een wat aansluit by Pieter se vraag rondom die hele doel was om die twee te toets en met daai wat ek net wil vra is ek dink jy het al gesê hoe wat die efficiency is, maar wat is jou gevolgwerking rondom dit? Moet almal nou eers die ou propeller weggooi en die nuwe tipe doen of
My gevolgtrekking is dat dit wel beter is, maar as gevolg van manufacturing, op die oomblik kan hierdie net 3D printed word. So dit gaan moeiliker wees, of as iemand dan nou 'n 5-axis CNC masjien het, dan sal hulle dalk dit moet maak. Maar vir iemand wat sê drones wil maak wat sagter dan nou is, in die toets het ons wel nou nie klank getoets nie, maar vir iemand wat drones wil maak wat sagter is, en wat heel moontlik beter kan op 'n lang afstand batterylewe langer laat hou, sal die ideale propeller vir hulle wees.
Persoonlijke vraag? Hoe te zien?
Ek is af.
Het jy enigstens gedink daaraan om nie 'n fix te doen, maar na te kyk om daai te kan doen repeat?
Dis so?
Die blade. Om dit miskien ook op 'n lang termyn te kan repeat op jou so dat jy
So 'n bracket, soos 'n constant propeller spier wat in die regte lewe in die vlieg kan roteer.
kan verander, ja.
Ja. Ek het gedink daaraan en op die ouend het ek besluit daarteen omdat ek nie eintlik bewus was van hoe baie werk ek kon regkry in hierdie termyn nie. En op die ouend het dit tot op die nippertjie gekom, so as ek een gemaak het, dan sou dit moontlik gewees het dat ek met 'n taakie gestaan het wat halfpad geprint was, ja.
En dit is fyn, dit is maar net
Iets om op te dink, ja.
dat ek die vraag weer wil hoor, want as jy dit kan regkry, die efficiënsie van daai blade is soveel beter, soos jy gesien het. So ja. En dan wil ek maar net ek maar in dit nou die tyd gee vir self vir die load cells installasie en so aan.
Ja.
Dit is baie mooi.
Dank je.